Hello and welcome to our group presentation. We are happy to present you the image processing engine with user graphical interface. Now let's take a look at the motivation and what we have achieved.
Imagine Bob is a researcher in computer vision. Now Bob wants to turn an RGB color image into grayscale. There are several ways he can achieve this. Use Python libraries such as Pillow, Pandas, or even OpenCV. Or he can use MATLAB, which requires installation and studying the language. He can also use Photoshop, which is heavy and expensive. Or ultimately, he can write a piece of program by himself. But none of the solutions above are convenient. Most of them has learning curves, and Bob has to learn hard. Some software are targeted at the photographers, which do not provide advanced functionalities like edge detection or depth estimation. Our solution is to create an image processing engine for researchers, which does precisely what they want in a portable way. They do not need to learn programming libraries in order to do image transformation. Rather, they can focus on the techniques themselves and forget about debugging the code. Here is our final product. We have 24 different image processing methods implemented, with easy-to-use GUI panel for each. On the preview panel, user can compare with the raw input by dragging the slider, click to compare in pixel-to-pixel level, or show a side-to-side view. While the resultant image can be easily exported for sure, the processing pipeline itself can be saved and used in the future to recreate the same effects to any images. Now we will demonstrate the key functionalities and transformation methods of our image processing software.
Thank you, Joey. When the program starts, we can see a simple GUI layout, and the Basic Actions tab is open by default. Here, for convenience, we've already imported a sample image, so feel free to use Import button on top to use your own. Some simple transformations such as inverse color, grayscale, flip horizontal or vertical can be applied to the image by just a single click, just like this. You can also see it appear down in the list of transformations here. Now on the right-hand side is the image panel. We implemented a very cool feature for users to compare what has changed to the image. We can use sliders. By default, it is on the top right corner. So when you drag the slider like this, it can show this region in original. You can choose different corner you want to show the image as well. You don't like sliders? Then just click this tab, and we can bring you to a parallel image view. You can then compare between two images more clearly. We can also change contrast and rotation of an image by dragging the slider and change its factor from 0 to 1. The image changes with the slider, so it gives us a very nice preview. If we want to save what we have done, then we can just click Apply. It will stack onto the list down below. The transformation list also gives us a redo and undo feature, so we can go back and forth the transformation we've applied so far. Now if we click Color Adjustment tab on the left, we can see 6 sliders. Here, that means we can adjust the image in RGB and HSV mode. So here we can increase or decrease the R value to change the redness of the image, and so does G, green, and blue. HSV stands for hue, saturation, and value. Using these measurements makes the image appear closer to what human eyes have seen. Last but not least, dragging the slider of black and white makes the image shown in only pure black and white, so giving a really strong contrast in the result. Now if we want to save the image, we can just click Export on the top bar, and the job is done. Now let's hand over to Henry, and he will introduce the program further.
So thanks, Stephen, for the demonstration. Now I'm going to introduce the following processes. The first one is sharpen. You see the image will look sharper because the highlights in those high frequencies. And the next one is the opposite, which is blur. You can choose from the range of kernels and also to select the kernel size. That will make the image blurry. Blurring is especially useful in computer vision because it can help like edge detection, so on. And the next one is blend. So we can pick a blend image and to choose from one of the 17 blend modes. just click blend. That will create a special effects of two images stacking on each other. And the next one is posterization, which is pretty interesting because it reduced the color map to make the image look like an old poster. We have also implemented resizing. So you can choose from those resizing methods. And we have also integrated the gamma aware resizing, which corrects the color space if we do a resizing. And that will make the image smaller. And next, we'll move on to Tom.
This part will cover some features that are implemented using neural networks. The neural style transfer feature is implemented by using fast neural transfer, which involves training a transformation net that will remember the style of an image. We have chosen 6 different style images and trained 6 different models for each of them using a paper whose link is available in the filter panel. A comprehensive training method is also included in the appendix section of our report. This is useful in the field of art generation. Next is depth estimation. This feature is also implemented using 2 open-source pre-trained neural network models. User can simply choose one of the models and then a color map to show an estimated depth. This is potentially useful in the field of computer vision, where a machine needs to understand the information of its surrounding environment. Next, stegnography. In our implementation, user can encode either an image or a piece of text in another image using the least significant bit method. Please refer to, again, our report for more detailed explanation. The software can also decode an image with hidden message in it. For encoding image, user can choose to select which bits to use and what encoding scheme to use. Watermarking is achieved using the least significant bit in the stegnography, as well as some blending methods. We could potentially add more ways to adjust the watermark, such as rotating or the way it should fill the input image. But we leave it for future development due to the time constraint. The next part is false coloring. False coloring will map the color palette of an image to another predefined set of colors. This will make some parts more distinctive than others, with a potential application in geology or city planning. Finally, denoise. Denoise is also implemented using a pre-trained model that can remove noises on the image. User can choose a drone net or adjust the noise level and use the read net to achieve this. The result image will look smoother. This is potentially useful in the field of image restoration.
In this part, we'll talk about frequency domain filter, histogram equalization, and visualization of convolution neural network. Starting from histogram equalization, the main concept of this algorithm is to collect the distribution of the pixel in a color space and stretch the cumulative density to a linear function. For example, when applying the grayscale histogram equalization, the image is first transferred to the grayscale image, and the distribution of a grayscale color is collected. The CDF is presented as a red line in the chart. After processing, the distribution of the grayscale value are stretched to a linear function, with the CDF presented as the orange line. As we can see, the processed image has greater contrast compared with the original image. This is due to pixels which used to be concentrated in the middle range of the color space are separated to take more extreme values of the color space. Also, other color space could be selected, and this will change the pixel distribution in the corresponding color space. For example, by equalizing in the red RGB space, the red pixel values are changed into a linear function. The other functionality is frequency domain filter. This algorithm transfers the image to frequency domain and selects the certain range frequency range before transferring back to the RGB image. The filter could be seen in the right-hand side of the panel, where the white pixel means that the frequency is allowed to pass the filter, while the black pixel means that frequency are not passed. They are blocked and not shown in the output image. Various of other filters are provided and could be selected in the box here. Finally, we also implemented the visualization of CNN, which takes the PyTorch neural network and allow user to select each layer's output. To use this functionality, user need to first give the shape of the input tensor for the network. Given that, we import the neural network. The component of the network will be displayed below. After selecting the certain channel number and select Visualize the image, the channel's output tensor will be transferred to a grayscale image and displayed. This tool is useful for understanding the behavior of CNN layers and experimenting with applying other image processing algorithms to the output of the neural network. Next, we will talk about edge detection and the features that improve the usability of the platform.
In addition to the features mentioned above, we also have our own implementation of edge detection. Our implementation uses a variation of the canny edge detection algorithm, which consists of turning the image into grayscale, noise reduction using a Gaussian filter, gradient calculation to detect changes in brightness, non-max suppression, thresholding, and edge tracking to connect the lines. This allows the users to visualize what the edges of their image looks like and may be helpful when debugging a higher level function. From using the software ourselves, we notice that often the same list of transformations needs to be applied to a number of different images. So we added the ability to export a list of transformations as a JSON file so that the same pipeline can be easily applied at a later date.
Furthermore, we also recognize that researchers often want to compare the effects of the same processes on different images. That's why we have implemented batch processing to help them achieve just that. Start with, say you have this sequence of transformations. First, you need to import all the required images, then click Apply All to begin the process. Each image undergoes the same transformations asynchronously, and after a few seconds, you'll be able to preview the results. When we have a lot of images, multi-threading really shows strength and improves performance massively. We hope that you enjoyed the brief introduction to our software. Now that you've seen what we built, we'd like to walk you through how we built it. As a group, right from the beginning, we have decided to follow agile development principles, whereby at the beginning of each iteration, we agreed on a number of features we wish to implement, taking into account suggestions from our supervisor. Then, we put these ideas into the to-do column in our Kanban board to kickstart the iteration. Along the way, as we get more feedback from the users, or as new ideas come to our minds, we can add more tasks here. Then, one person would assign the task to themselves as a way of claiming responsibility to implement that feature and move it to appropriate column as they make progress. This also allows other members to keep track of their progress as well as the progress of the whole project. When the task is completed, they'll need to create a merge request into our designated development branch. For minor changes, we require at least one member to approve it before it can be merged, and we encourage more people to be involved for breaking changes. At the end of each iteration, we make sure everything compiles and runs as smoothly as possible before merging it to the master branch.
We have also thought about potential future development based on the current state of our software. We could implement more processing methods such as morphing, interest point detection, object detection, and image segmentation. We could also design more GUI functionalities to improve the user experience, such as layers and process bus for tasks with long processing time. We could also plan on applying more methods for accelerating the processing. For example, in hardware, we could make use of GPU, and in software, we could use pthreads from C libraries, which has more significant improvement in multi-threading algorithms. And finally, we could design a methodology to stabilize the user experience and performance of the general software.
During the development process, we have been collecting suggestions from our supervisor and improve application accordingly. For example, the frequency domain method was emphasized in the initial proposal and mentioned after the first milestone. Thus, it was implemented as a prototype in the second iteration and refined in the third. Multi-threading was also a field we explored in several algorithms. However, due to the limitation of the Kotlin language, which has high overhead when multi-threading is applied to even simple processing methods, we have to decide to move it for future development as it requires to link C libraries such as pthread to Kotlin. During the development process, we have also adopted the model view controller model, which separates the responsibilities between the view and model. This enables us to test out the performance of each processing method, which is also attached in the report appendix section, without depending on the view. Furthermore, the model view controller makes adding new features a lot easier by just following a clear sequence of steps to add new features.
Overall, our software has achieved what it set out to do and could be used in various scientific research areas. With an easy-to-use interface, the user can clearly know what the software is doing behind the scenes and allow these algorithms to be used by everyone, not just those who are proficient in coding.